So my goal for today is just to wrap up our discussion of Bodie plots. And so we have kind of one last set of things to look at here. To this point, I believe we have covered zeros at the origin, poles at the origin, simple zeros, simple poles, and kind of looked at what would happen if we had a repeated zero or pole. So now we're going to talk about complex conjugate poles. I can't spell conjugate this morning, apparently. Conjugate, there we go. All right. So let's say that we have a system whose transfer function is described as follows. In the numerator, we're just going to have some constant c. We'll talk about that in just a second. And then down here in the denominator, we are going to have a second order polynomial in S as follows, right? So the c in the numerator and the c in the denominator are meant to be the exact same constant here, so that when we put this thing in standard form, our numerator is just going to look like the number 1. Okay. So what kind of system would be described by this type of transfer function? Really, any second order system is possible to be this type. So we're really just thinking about cases where we have two discrete energy storage elements in our system. Okay. So I'm going to expand this out where I'm going to have in my denominator first, we're still going to just have S squared. And then I'm going to put that B coefficient and write it in a new form. So this is going to be 2. And I'm going to pre-apologize that I cannot write the Greek letter zeta to save my life, but that's what this is supposed to be. Zeta times omega naught S plus omega naught squared. And since C is just omega naught squared, I'm going to put omega naught squared up here in the numerator as well. So in this particular expression, omega naught squared is simply equal to C, which is the resonant frequency of the circuit. Do any of you guys remember from circuits 2 what the resonant frequency means? It is the frequency at which the impedance of our system is purely real, meaning all of the positive reactance that's contributed by inductors is exactly canceled out by all of the negative reactance contributed by some capacitance, right? So in order for us to have resonance, we must have two independent energy storage elements, and the reactances are canceling each other out. Our coefficient zeta is going to be equal to B over 2 times the square root of C from our coefficients above. And this is what's known as the damping factor of the system. And it is usually related to the amount of resistance in our system in some way, shape, or form. So what we're going to do now is we are simply going to divide through our numerator and our denominator by a factor of omega naught squared, so that we can have our constant term in our denominator as 1, which is the standard form we usually use to write our Bode plots or to draw our Bode plots, right? So that means that the standard form of our transfer function will now be 1 divided by, so I'm going to have s squared over omega naught squared. I'm going to choose to write that as s over omega naught quantity squared plus twice zeta times s over omega naught plus 1, like so. So now we're going to talk about how zeta informs the behavior of this transfer function. So let's first consider cases where zeta is greater than 1, okay? So specifically here, we're going to mathematically look at zeta is equal to 1.25 because the math will come out easily in this case. Okay. So for zeta is equal to 1.25, our transfer function would be h of s is equal to, let me do my denominator first, s over omega naught quantity squared. 2 times 1.5 is just 2.5. Or excuse me, 2 times 1.25 is just 2.5. S over omega naught plus 1. And our numerator here is just 1. Well, this thing can be factored, right? So to me, what two numbers can I multiply to each other to get 1 and add to each other to get 2.5? Well, that would be 1/2 and 2, right? So this is going to look like, as a denominator, 1 plus s over twice omega naught multiplied by 1 plus s over half omega naught. And for any zeta that is greater than 1, we will wind up with a situation like this, where we are going to have 2 distinct real poles. How do we treat a system like this? Just like we've done previously, right? So we know that this pole is going to contribute, it's going to look like 0 dB until we hit our pole frequency here, which would be whatever twice omega naught is, and then it's going to roll off at 20 decibels per decade. Daniel, that may help you. Probably. Actually, does it matter? When I divide by 0.5, that looks like a 2 in the numerator. When I divide by 2, that looks like a 0.5 in the denominator. Ha ha ha, I got you. And actually, I think I prefer it this way because we can see how it's affecting our pole frequency. Yeah, I did it the way I wanted to. So anyway, right, for this guy right here, we have a pole frequency of twice omega naught, so it's going to be 0 decibels up until that point, and then it's going to roll off at 20 decibels per decade. For this guy right here, we have a pole frequency at half omega naught, so it's going to be 0 decibels up until that point, and then roll off there, right? So we would just add those two responses together. Easy peasy, we've covered this before. Our phase responses would just add together like we've done previously as well. So literally nothing is new. So now let's look at what happens when zeta is exactly equal to 1. Right? So what does our transfer function look like? Well, now we're going to have s over omega naught squared plus 2 times s over omega naught plus 1. This can also be factored, but now we have a case where we have a repeated pole, right? So this is just going to look like 1 plus s over omega naught quantity squared, which is just a special case of the condition above, right? Our pole frequencies for each contribution are at the exact same place, so it's going to look like effectively 0 decibels up until we hit this frequency omega naught, and then we're going to roll off at negative 40 decibels per decade. So for every number greater than 1 and including 1, this is all cases that we've dealt with before. Okay. Well, when zeta is between 0 and 1, we have complex conjugate poles. Okay. So if actually 0 is less than zeta is less than 1, we will have complex conjugate poles in our system. So let's look at what our transfer function is going to look like specifically here, right? So I'm going to look at h of j omega. So I'm simply substituting in s is equal to j omega. For every other instance that we've had, we didn't really need to do this. Yes, Gracie. So we will look and see what happens when zeta is equal to 0. And for those of you that have, well, actually, we'll look at what happens as zeta gets progressively closer to 0 and what the implications of that would be. And then how many of you guys have seen Fourier transforms before? A couple of you, okay. This will actually explain why pure sinusoidal functions and pure cosine functions look like impulses in the frequency domain when you're dealing with Fourier transforms. So it technically can. That being said, for any physically realizable system, it won't ever be that because there's always going to be resistance because there are wires and things like that. So we can get very, very close to 0, but we can never get exactly to 0. All right, so h of j omega. So that's going to look like 1 over j omega divided by omega naught squared plus twice zeta times j omega over omega naught plus 1. We know that j squared is equal to negative 1. So really this is going to look like 1 plus j times twice zeta omega over omega naught minus omega over omega naught squared, and that's my denominator. Okay. Legitimate question, do you want me to manipulate this further so that we can get the phase response, or will you trust me that my phase response is correct? Okay. So we'll leave it like this, just so we don't spend 5 minutes doing complex math that's not particularly difficult, but just wasting time. All right, so let's talk about how this thing is going to behave. So what do you think this is going to look like when omega is much less than our resonant frequency, omega naught? These two terms are going to be very small. It's going to look approximately like 1/1, right? So let me scroll down here. So when omega is much less than omega naught, h of j omega is approximately equal to 1, and therefore 20 log of the magnitude of h of j omega is approximately 0 decibels. What happens when omega is much greater than omega naught? Well, our omega over omega naught squared term in our denominator becomes the most dominant contributor to our system's frequency response, right? So it's going to look like 1 over omega naught quantity squared, right? So h of j omega will be approximately negative 1 over omega naught quantity squared. Just so that we can wrap our heads around things really quickly here, what if omega naught were 1? This would look effectively like 1 over omega squared, or just 1 over s squared. What would a response for 1 over s squared look like? Frequency response. What are we going to see? We're going to see a decay, or we're going to see a slope of negative 40 decibels per decade because we have a repeated pole, right? So 20 log of the absolute value, the magnitude of h of j omega, as a slope of negative 40 decibels per decade, and it'll start that roll off at omega naught, our corner frequency, our resonant frequency, whatever you want to call it. So it looks like it behaves very similarly to what we would expect for a simple repeated pole, right? But what happens when we're really close? Omega is very, very close to omega naught. Yes. No, it's valid for anything. So if omega naught isn't equal to 1, our corner frequency just gets shifted to whatever omega naught is, just like it happened with our case of simple poles, right? So it's just going to slide that graph left and right, depending on where omega naught is, but we're still going to see that it's got a slope of negative 40 decibels per decade, because it's behaving as if there were a repeated pole, because we have something that is dominated by 1 over omega squared. Yes. So we will see that in just a moment. But realistically, 2 to 3 times larger is enough to where it'll start getting back to this case. and 2 to 3 times smaller is where it'll start looking approximately like this. Exactly like everything that we've done before, right? So all we've done at this point is established effectively our asymptotic limits for what this thing is going to look like, which is exactly what we did when we had a simple pole and a simple zero. It was, for a simple pole, it was 0 decibels until we hit our corner frequency or whatever value of S gave us a pole, at which point it rolled off by 20 decibels per decade. Here we're seeing practically the exact same thing, except that because the pole is repeated, it's rolling off at 40 decibels per decade. Hannah, what was your question? Yes. So now, let's talk about what's going on when omega is approximately equal to omega naught, or for our case, exactly equal to omega naught. So when omega is equal to omega naught, we have this term right here would be omega naught over omega naught squared. So that's just going to look like 1. 1 minus 1 is 0. So it's dominated by this middle term, right? One over 2 zeta, because the omega over omega naught bit here is still just going to look like 1. So the only thing that matters is zeta. Yes. Actually, that should be there. But we're going to deal with magnitude, so it's not going to matter in a minute. Effectively, all that J is telling us is that at this exact frequency, our phase angle is 90 degrees. Just like up here, right here, this negative sign is telling us that when omega is greater than omega naught, our phase angle is 180 degrees. And over here, the fact that this looks like just 1 is telling us that our phase angle is 0 degrees until we get close to our corner frequency. So without ever actually looking at what the phase response is formally supposed to be, we already have an idea of what it should be doing anyway, just by looking at the signs and then the presence or lack of that J term. All right, so I want us to develop a table. Do it out here. So since our response is dominated by this term, I'm going to put, that's just the letter Z, which isn't what I'm looking for. So we're going to put zeta on this side, and then 20 log of the magnitude of 1 over 2 zeta here. So when zeta is equal to 1, we have 20 log of 1/2, right? 20 log of 1/2 is negative 6.02 decibels. And so this is effectively telling us what correction we are going to have to make in the area of omega is equal to omega naught to make our graph as accurate as possible, okay? So effectively, for a system in which zeta is equal to 1, we need to make our graph hit negative 6.02 dBs lower than 0 dBs, which was what our starting point was, as it trends towards that negative 40 decibel per decade slope. We'll draw that out in a minute. Now, let's look at what happens when zeta is equal to 1/2. So at 1/2, we would have 20 log of 1, which is 0 decibels. So effectively, if zeta is exactly equal to 1/2, we don't have to correct anything. For 0.25 zeta, we're going to have 20 log of 2, 20 log of 2 is positive 6.02 decibels. For 0.1, that's going to look like 20 log of 5, right? So 20 log of 1 over 0.2 is the same thing as 20 log of 5 because 1 over 0.2 is 5. So 20 log of 5 is 13.979 or about 14 decibels. We go a little bit smaller, 0.05 is going to give us an increase of exactly 20 decibels. And let's do 0.01. So this is going to look like 33.979 decibels, and so on and so forth. So to answer Grayson's question from earlier, what would happen if zeta is equal to 0? Our response at omega naught would go to infinity. We would have an impulse function at that specific frequency. We will never really be able to achieve that because our system will always have some damping factor. Any physically realizable system will always have some sort of resistance. So, as I mentioned a moment ago, these are just corrections to the response that we have already figured out, okay? So let's put this into practice by drawing our frequency response curves for these various values of zeta. So over here, we're going to have 20 log h of j omega. Here is our omega axis. Let's make this guy right here omega naught. So this guy right here would be 0.1 omega naught. This guy over here would be 0.01 omega naught. Over here, we would have 10 omega naught. Out here, we would have 100 omega naught. This curve that I'm drawing in red will be for zeta is equal to 0.5, where we don't have any correction, okay? And I need to set the limits on my scale here. So this will be positive 20 dB, positive 40, negative 20, negative 40, like so. So we would have something like this, where 0 decibels until we hit our corner frequency, and then we are going to decrease at a slope of negative 40 decibels per decade. So something like that. Now, in this green color, let's superimpose on top of here what it's going to look like when zeta is equal to 1. So we know that at zeta is equal to 1, we have to correct by lowering things, negative 6.02 decibels. So that's going to be a point that's approximately here. And so our curve is going to match until we get around our corner frequency, and then it's going to roll off, pass through that point, and then meet back up to continue that negative 40 decibel per decade slope that we expect when omega is greater than omega naught. Let's do this light blue color. For zeta is equal to 1/4. So at zeta is equal to 1/4, we should have a correction of positive 6 decibels. So a point about right here. And so what we're going to see is it's going to increase, pass through that point, and then decrease rapidly until it falls back in line with that slope of negative 40 decibels per decade. And all of our subsequent points are going to look like that as well. It's just the increase gets larger and larger, right? So for zeta is equal to 0.1, we had about 13 decibels per decade. So that's about right there. For zeta is equal to 0.05, we had a 20 decibels per decade. And let's see what color. I can do blue. For zeta is equal to 0.01. That was at about 33. So that would be somewhere about here. Like so. So we really have a family of curves here that are all effectively the same, except for the correction that occurs around omega is equal to omega naught. Brody. Do they all start? Yes. And so, like this should actually probably be narrower. We're going to talk about a thing called the quality factor of resonant circuits in class on Wednesday. Effectively, what we're going to see is that zeta and the quality factor are inversely related to each other. So systems that have a very high Q value, quality factor, have very narrow bandwidths. Why are you guys shaking your head? Have you talked about this in other classes or something? Or
just doing it in our lab.
Oh, great. Okay, so Q, the quality factor, is related to this damping factor, except that they're inversely proportional to each other. There's a little bit more math behind it than that. Quality factor has something to do with the amount of energy lost in a single cycle of oscillation for the system versus the energy stored. And we'll mathematically derive all of that kind of stuff. But effectively, for certain applications, you want a very, very high Q factor. And for other applications, you don't. So honestly, I can't think of anything that you would want to resonate with a low quality factor off the top of my head. But if you wanted a resonator with a very high quality factor, a good application for that would be a radio or something like that, right? So the higher your Q factor is, the higher your selectivity is. So you get really, really good response, amplification really, at your resonant frequency. And then for all other frequencies, you pick up nothing, right? So when you think about a car stereo or something like that, right? You have an antenna. The length of the antenna is probably, for FM radio signals, probably several wavelengths long, right? When you get into your fields classes and all that kind of stuff, you'll figure out why that's it. But you guys have had physics 202, right? So what does the electric field density do as a function of distance? When you get further and further away from the origin point of an electric field generator, what does the field strength do? 1 over R squared, right? So it decays the further and further away that you get from the source. So if you're trying to pick up a radio station from Shreveport or Bossier area, and you're over here in Ruston, what do you think the field strength is? Probably millions of times smaller than where it's at, what the field strength is at the broadcast tower or something like that, right? So you want a system like your tunable radio system to have a very, very high quality factor so that when you're trying to pick up a signal at, let's say, 98.1 megahertz, which is 98 Rocks, the classic rock station I listen to driving into work, you want a very, very high quality factor or a very, very low damping ratio so that signals at this specific frequency get boosted by a factor of tens of thousands to a few million so that you can actually pick up that station while not picking up every other station at the same time, right? So Q factor is all about the selectivity of the system. That's also why like your filters and all that kind of stuff in your cell phones have extraordinarily high Qs because the digital telephony bandwidth is pretty small, and then it's even smaller for each channel so that Andrew can't pick up Daniel's phone call or something like that, even though their cell phones are operating at effectively the exact same frequency. So where was I going before I got distracted? Okay, so this is what our magnitude response effectively looks like. And the lower the damping function gets, the higher and higher this peak goes, and the more narrow this thing is, giving us a higher quality factor and all of that kind of good stuff. All right. So now let's talk about, or actually before we move on from this, does anybody have any other questions or anything? Okay. So now let's talk about the phase response. So, bless you. All right, let me scroll up here because I didn't bring my notes for this part, so I have to remember what the phase response is going to look like really quickly. I think if I multiply this thing by its complex conjugate, I would have 1 minus this in my denominator and that in my, okay, good. So the phase response as a mathematical function, phase angle as a function of j omega is going to be equal to the negative, the arctangent of negative 2 zeta times omega over omega naught divided by 1 minus omega over omega naught quantity squared. So we can see that at very low frequencies, effectively we're going to just have the arctangent of 0 over something close to 1. Well, the arctangent of 0 is 0, right? So we should see, we plot this out. Let's put positive 180 here, 90 here, 0 here. Negative 90 here, negative 180 degrees here. Let's see, omega naught, 0.1 omega naught, 0.01 omega naught, 10 omega naught, and 100 omega naught. So up until we get to about a tenth of omega naught, we're going to be at a phase angle of 0 degrees. And then out beyond 10 omega naught, we're going to be at a phase angle of negative 180 degrees. Exactly the response that we would expect from a second order repeated pole. And then the value of theta is going to have some influence on our phase response as well. Okay. So for zeta is equal to 0.5, which I believe I used the red color for zeta is equal to 0.5 earlier. I'm trying to be consistent. We have effectively the exact same response as what we would expect. So it should hit negative 90 degrees at exactly our resonant frequency. It starts decaying at about 1/10 of our resonant frequency, and it hits its value of negative 180 at about 10 times our resonant frequency, exactly like what we would expect for a repeated pole, right? So for a single pole, it's doing the exact same thing, except that it hits 45 degrees or negative 45 degrees at that corner frequency. Well, as theta gets smaller and smaller and smaller, let's see, what would be the next color that I would have? Light blue. We're going to see that it's doing effectively the same thing, except that it goes a little further. Like so. Next color would be light purple. So effectively, it's just transitioning from 0 degrees to 180 degrees faster and faster and faster. And then if we were ever able to physically realize the system with a damping factor of 0, we would see an instantaneous transition from 0 degrees to negative 180 degrees exactly at our resonant frequency. Okay. All right, so let's put together an example problem really quick, and then that'll be enough out of me for the day. So let's say in my denominator that I have a factor of 1 plus s, and then I'm going to have s squared plus, let's say, 10s plus 10,000. And then up here, I have 100,000 s. So how am I going to get this thing? Or actually, let's rephrase that. What should my first step be? Put it in standard form, right? So I'm going to divide the numerator and the denominator by a factor of 10,000. Okay. So that means I'm going to have 10s in the numerator. And then I'm going to have 1 plus s out here. So let's see. So this will be, what's the square root of 10,000? 100. Good. I did the right number of zeros to where this isn't going to have a dumb square root of 10 in there and mess everything up. Great. So that's going to look like S over 100 squared. So let's see, 10 over 10,000 looks like 1 over 1,000. I'm just going to come out here on this side and write this out. So B is going to look like 1 over 1,000. C was 10,000, which means omega naught is 100 because that's just the square root of C. Zeta was B. That was our original B. Well, now I'm shit. Hold on. B was 10. Sorry. C was 10,000. Omega naught is 100, which is just the square root of C. Zeta is B over 2 square root of C. So B would be 10 over 200. 10 over 200 is 1/20th or 0.05. So 2 times 0.05 times S over 100 plus 1. Close that guy out. Okay, I believe I've done that in the right. So I'm trying to put it of the form to where I can explicitly see what zeta is and all of that kind of good stuff so that I know exactly what's going on. Okay. So I can see that I'm going to have 3 distinct parts to my frequency response, right? I'm going to have it, well, technically, I guess you could call it 4, because I could have a part for the constant value of 10, a constant for, or excuse me, a bit for a 0 at omega is equal to 0. I'm going to have a pole at omega is equal to 1. And then I'm going to have this guy right here, which looks like a pole, excuse me, the frequency response for complex conjugate poles, where zeta is equal to 0.05 and omega naught is equal to 100 radians per second, right? So let me draw out all those individual parts. So this will be 10 to the 2, 10 to the 1, 10 to the 0, 10 to the minus 1, 10 to the 3, 10 to the 4. That should probably be enough. Here's omega. 20 decibels, 40 decibels. Scroll down here. Negative 20 decibels. Negative 40 decibels. All right. Actually, I have it 3 per division up above, so I should have it 3 per division down below, or that's going to look real awkward. All right, so let's do the constant term first, and I'm going to do it in orange. Right, so what is 20 log of 10? Why is it taking you so long to say 20? 20. Yeah, 20. So 20 decibels, right? So the constant term or the gain, overall gain of the system is going to look like 20 decibels with a phase angle of 0 degrees, right? So it's 20 dB across everything. Then we have our 0. Let's do that in red, right? So the S by itself. So we should see that it crosses the horizontal axis at 10 to the 0. And it's going to cause an increase of 20 decibels per decade because we're dealing with a 0. So that means we're going to have this line. Like so. Then we have our pole, our simple pole, this term right here, which happens at also 10 to the 0. And then we have our complex conjugate pole, which happens at 10 to the 2. So let's see here. And our zeta was 0.05, so that should be a correction of 20 decibels. Look at the table if you want to double check that, or if you tell me I'm correct, would be better. Zeta 0.05 equals a correction of 20 dB. Okay. So let me something like that. And now we add all these bad boys together. Let's do it in this dark gray. All right. So way out here on the left-hand side, we have 20 decibels being counteracted by this bit right here, which is just a little bit more negative than negative 20 decibels. So I think it's going to start out around here, right? And then from this point, I have 20 dB, and then this is getting, so I'm adding this and this together. So it's still going to continue to increase. It's actually just going to be this curve shifted up by 20 dBs would be the easiest way to look at it, right? So I should hit about there. Now, this slope and this slope are canceling each other out. I've got this bit is contributing 0 decibels, so it should just stay constant for a while. I get close to that corner frequency of my complex conjugate pole contribution, at which point it's going to jump up by 20 dB. Jacob, you raising your hand? I may be just 20. I might have just drawn that slope slightly too positive. Yeah. So if we look at this exact point right here, we have 20, 0, 0, 0. Yeah, so you're right. It should just be 20 decibels right here. So I just drew this line a little too steep. Okay, thank you. Out to here, this should be 20 decibels up. And then Yeah, at this point, I should be 20 decibels, and this is the 40 dB per decade bit. And then keep on trucking like that. So something like this would be my hand-drawn approximation of this guy. So what kind of filter would this be? A bandpass filter. But realistically, it would only be a bandpass filter based on the conventional definition from about here to here, right? So if this were, that line were positive 37 decibels, this would be our half power frequency on the left-hand side. This would be our half power frequency on the right-hand side. So our bandpass filter operation is really only like here. All of this business going on down here doesn't really do anything. All of this business going on down here is just it getting more and more negative. So while we do have amplification from the conventional definition of a bandpass filter, where our peak value is our corner frequency, and then 3 decibels lower than our maximum amplitude is what defines our bandwidth. This is actually its only place that it's behaving as a true bandpass filter. And we'll talk about that a little bit after we talk about resonance. So we're going to talk about resonance on Wednesday, and then we're going to start talking about filters again past that and get into filter design and all that kind of good stuff. So anyway, all right, we're wrapping up about 15 minutes early, but yes, Hannah. Sure. So let me go up here to the top, and then I'll put this there, and then I'm done. So the orange line is for the constant. The red line is for the 0 at 0. The light purple line is for the pole at 1. And then the blue line is for the complex conjugate poles at 100. Do what? 10. Yes. Got that, just to be really clear, by dividing this 100,000 by this 10,000. Right, absolutely right, yes.
Like that.
Right, so 10 gain, whatever, we didn't specify if this was a voltage gain, a current gain, a transconductance gain, a transimpedance gain, or anything like that, but 10 gain in a volt per volt scale is 20 decibels. Right, so a standard, yeah, so a simple pole or a polar, so a simple pole or a simple 0 just gives you 0 decibels until you hit that particular pole's break frequency is what it's called. And then if it's a 0, it increases by 40 decibels per decade, and if it's a pole, it decreases by 20 decibels per decade. And so that's what we see is going on with that light purple line, right? We're at 0 decibels until we hit our break frequency, and then we fall off. The red line, you might want to stand up and getting real loud. So this light purple line is because we had a pole at omega is so 0 decibels until we hit omega is equal to 1, and then it rolls off. And then it's red line because we have a 0 at omega is equal to 0. So we know that it should have a value of 1 at omega is equal to 1, which is 10 to the 0. Passes through here at 10 to the 0, and it's increasing at a slope 40 decibels per decade. So the poles being the zeros that aren't at zero pass through. So like there's a difference between a simple pole and a pole at zero. A simple zero and a zero at zero. And I know I'm saying a lot of weird things. So when we had a pole on the origin of the system described by a transfer function of just one over s. So this is a pole that we pass through at one. And this line extends with a slope of negative 20 decibels per decade. Whereas when we had a pole at a So this is a pole, a simple pole at dot. So we go out to our break frequency, 0 decibels until we hit the break frequency, and then it's decaying at a slope of negative 20. Zeros is literally just this graph flipped over the horizontal.
Right, okay.
So that's where this bit came from, having a 0 at the origin. This bit right here, having a pole negative 1. This bit right here comes from our constant values. And then this bit right here with the if we had conjugate zeros, it would be the exact same thing, except if we flipped over, we would have a dip down. No.
The difference between the red and the purple.
So the red line is for a 0 at the origin. So we can see that it's a 0 because it's increasing with a slope of 20 decibels per decade.
Right.
And it was at the origin because it passes through 10 to the 0 and keeps on going. Whereas if it were a 0, so if instead we would have had something like, let's do S plus 10 in the numerator. In standard form, this would look like 1 plus S over 10, right? And so for something like that, let me do it in this bright green color. It would be 0 decibels until we hit 10 to the 1, and then it would increase at a slope